graphs, and we did logarithmic graphs. And now we're going to see why those things are useful. These are some situations where these graphs are useful. We talked a little bit about them yesterday. So graphs that are exponential graphs are like this. Up like that. Or they down like that. People refer to them as like exponential growth or exponential decay. So population, for instance, usually follows a curve like this right here, where population grows and grows and grows, and then it just like starts to spike. And if you think about it, it makes sense. The reason why it makes sense is if you started off with just 2 people, and then they were each to have 2 kids, right? Then you only have 2 children. But then each of them went off and had children, and you could have 2 more children off that. And then think about a family tree, like how fast that branches off. It just starts with like 1 person on top, and then it's like kaboom, and there's all of a sudden 100 people underneath it. Same idea, just on a way larger scale. So if you think about generations and generations that keep going, that's why you have exponential growth when it comes to population. Same idea happens with bacteria, except bacteria is usually a much faster scale. So a bacteria will be like, oh, there's 1, and then a minute later there's 30, and then a minute later there's like 900. Like bacteria just kind of goes really fast. If you've ever seen something get moldy, which I've lived on my own, so I've watched a lot of things get moldy, that's exactly what happens. Like, starts off with a little bit of mold, and then all of a sudden it's like the next day, it's like a hole, it's a big spot, and the next day it's all of your whole loaf of bread. Yeah. And then you leave it for another month, and it just turns into nothing.
Yummy.
Financial growth is often the same way. So we're going to look at different types of financial growth. So sometimes it's positive financial growth, but sometimes it's negative financial growth. And then we're also going to talk about, those are all usually ways of growing. We're going to talk about decay, which is usually like asset depreciation. Think about vehicles. Like if I buy a car that's worth $20,000, the next year it's probably worth like $18,000. And then the next year maybe it's worth like $15,000, and the next year all of a sudden it's only worth $10,000, and it loses value really quickly. And that would be the same idea, except it would be decay. A, B, and T. So our formulas look like this. And A, B, and T all represent different things. Okay. Let's start with A. This is what it usually means. Okay? Not always, usually. A is usually a starting value. So for instance, if I was to buy a car at $20,000, that would be the starting value, it would be A. You might hear the term present value or something like that. It just means the value of something when you got it. Or an initial value. And G is going to be your rate. So if you're increasing, so if you had a rate that was getting better, that rate would be greater than 1. But if you had something decaying, so it was becoming worth less, it would be less than 1. We're going to talk about that a lot. And T, we just call that time for now. We're going to have to talk a little bit about it. Sometimes the time's not as obvious as you think it would be. Alright, let's do some questions. Example 1. The population of a specific type of bacteria growing in a petri dish is just like a little circular dish, can be modeled by the function P of T equals 700 times 5 to the power of T divided by 6. Where P of T is the amount of bacteria and T is the time in hours that have passed. So, P of T is how much bacteria you currently would have. If you're looking at this formula, 700 would be how much you started with, and 5 would be your rate of growth. So it's going to go increase by 5 every time your time goes up, 1 full period. Notice that time isn't just T, it's T divided by 6. So that means for this thing to actually increase to 1 entire period, it would have to be T equals 6. So then 6 divided by 6 would be to the power of 1. Right after 12 hours, 12 divided by 6 would be 2, so then you would have doubled it, right? It would have been 2 full periods of growth. Let's just do these questions and see if we can figure them out. Question A says, how much bacteria is there after 10 hours? They're always going to give you one of your variables. Did they give you P or T in this case? They give you T equals 10. So you just have to go into your equation and change T to be 10. You might see it written like this. So why did I replace T with 10? Notice that I also replaced the T that was attached to the P. This does not mean P times 10. This means P at time 10. So you don't need to do any division or anything crazy like that. This means P at time 10. It does not mean P times 10. So P at times 10, the amount of bacteria when T equals 10 is equal to, you're going to have to put that in your calculator. So you have 700 times 5 to the power of 10 divided by 6. So 700 times 5 to the power of 10 over 6. So that means the amount of bacteria that's rounded would be 10,234. A lot of bacteria after only 10 hours. Went from 700-ish all the way over 10,000. Shows you how fast things grow. Good question. I was hoping somebody said something. Like, no way you guys put that in properly. So, to put that in my calculator, what I did was I put in 700 times, so we'll start, bracket, 5, and then I did the little hat, so depending on your calculator, some of you, it actually puts you into the exponent. If it actually puts you into the exponent, you can just go 10 divided by 6. If you have a calculator like mine, that means you need a little hat symbol. The hat symbol is the one that's above the division sign. And then bracket, 10 divided by 6, and then double bracket close it. So that's saying 5 to the power of 10 over 6. And notice how that whole thing is in a bigger set of brackets. Because you're saying I only want the 5 to be to that exponent, not the 5 times. Yeah.
If you didn't multiply, like, you do 700 times, and you said 700 in the parentheses, would it?
That should be fine. Alright. E. After how many hours will the bacteria reach a number of 87,500? So now you're looking for time because they gave you what P equals. So that means we have 87,500 equals 700 and then 5 to the power of T divided by 6. There's two ways to solve this. Easy way and hard way. See that? We can just say something hilarious that none of you guys will know, and it's still happening. There's the easy way and the hard way to solve this. If you're trying to solve for an exponent, what did we learn that you can do to solve for exponents you don't know? Starts with melon, it rhymes with hogs. You can log both sides, right? You could try to solve this thing using logs, and it would work, right? So you would have to divide the 700 to the other side, log base 5 both sides, change it over. It would work. That's the algebraic way of doing things. It's the second way to do things. And I think you will enjoy this much more. So, for any question that you get where you have to solve something, where you have something equals something, you can graph it. Where that goes in your y1, and this goes in your y2. And this actually works for everything. If you're ever trying to solve two sides of an equation, you can actually just graph it y1, y2, boom, Bob's in. So, we're going to try graphing this. So I'm going to put this guy in for y1, so 87,500. And for y2, I'm going to put in this whole equation. I'm going to put it in the same way I put it up here, but with a t instead of a 10. So I'm going to go 700 times 5 to the power of brackets, x divided by 6. Close the brackets twice. And then I'm going to go to my window setting. And the window settings are the only place that this thing gets really challenging. Okay? So we need to set window settings that make sense for this question so that we're actually able to solve it. If you were to think about this, that's the best way to do it. What represents x in this question? X was t. What is t? Time, right? T is time. So what's the least amount of time that could pass? 0. So x minimum of 0 makes a lot of sense. Because no time can pass, right? You're not going to have negative time, so you don't need to worry about looking back there. Just say time equals 0 is your minimum amount of time. What's the most amount of time you might be doing this experiment? It's in hours, so that should be somewhat of a hint. We also know that after 10 hours, we were already at 10,000. So this is
100 hours?
Sure, let's try 100 hours. So put in 100 as your maximum hours. Again, that's a rough estimation. Okay? What I wouldn't do is I wouldn't put 2 hours, because that wouldn't make any sense that we would only do this for 2 hours, since we've already seen 10 hours gets 10,000. I wouldn't put in like 1,000,000 hours, because that also does not make sense that I would do an experiment for 1,000,000 hours watching bacteria grow. Kind of crazy. The scale, I always leave it as 1. Like, feel free, if you like to see your graphs differently, you can change that to be like 10. All that means is that your x's are going to count up by 10 along the x-axis. I just always leave it as 1 for some reason. Y minimum. What does y represent in this question? If you're looking at this formula, y is p, and what does p represent? The amount of bacteria. So what's the least amount of bacteria you could have? 0. So y minimum of 0 is plus. Y maximum? 90,000 is a great number. Why did you choose 90,000?
Because it's rounded up from 87.
Yeah, we're trying to figure out when 87,000 happens. So y maximum doesn't have to go much above that. I'm going to make it 100,000 just because I want to easily see where 80,000 is, or 87,000 is. But 90,000 is also a great answer. And we're using our clue of, well, we're trying to find 87,000, so it's got to be up there somewhere. Again, I can leave my scale as 1. Like, you can definitely change that to be like 1,000 or 10,000 or whatever you want. When I do that and I graph it, I end up getting a graph that looks like this. So you should get an exponential graph, like that red one, and then a straight blue line across. If you didn't get the exponential graph, that's likely the one you didn't get, you probably didn't put the y2 in properly. Make sure you use your brackets and everything like I did up here at the very top of the page. If you didn't do that, then maybe you made a mistake. Make sure you also have t divided by 6, not just t. That's also going to be important. For what, sir?
We don't, do we not substitute t for t?
No, you're trying to graph the original function. So this is like a whole new question. So it should be an x instead of a 10. That's a good question. Right, you're trying to solve this equation right here, so it would be t over 6. So, what this represents, the red graph represents my growth. You can see how quickly that bacteria grows as time moves on. What the blue line represents is where the bacteria would equal 87,500. And if you wanted to figure out the time when this red graph was at 87,500, you'd be looking for where they cross each other. So you would go second, trace, intersect, which is the fifth option, hit enter, 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 and you get that point is at 18,87,500, where X is time, Y is your population of bacteria. The answer would be 18 hours. So after 18 hours, that thing grew all the way to 87,500. It happens really, really fast. Exponential growth always happens really, really fast. There's like a famous exponential joke about how to become a millionaire from your parents. So the deal is that they're supposed to give you $1 to do all the chores for a day. And then the next day you do all the chores, they're supposed to double it. And then the next day you do all the chores, they're supposed to double it again. And so you would get $1 the first day, your parents were like, yeah, that's a sweet deal. And then the second day they have to give you $2. And they're like, yeah, it's still a sweet deal. We got all the housework done for $2. Then the next day they have to give you $4. And then the next day $8. And the next day $16. And if you do that 30 times, then by the end of the month they have to pay you like $500 to do the chores or something crazy like that. That's exponential growth, right? That's why these things grow so quickly, because you're multiplying all the time.
Yeah. So this thing was, would you rather get $1 billion right now, or for an entire 6 months, start with $1 and have it double every single day?
Yeah.
And you get $1 billion if you just took it. If you doubled it, you get something like $3 billion.
Way more. Yeah, it's exponential growth, right? Like it just will blow up because eventually you're multiplying numbers that are so big that you're now getting ridiculous pain. All right, let's try another one. So this one is going to be exponential growth, but it's going to be bad exponential growth. I heard the whining of, why don't we learn anything real in this class? So this is a real example of something that actually happens. So George has $3,200 on his Visa. That's not that much for a Visa bill if you've ever talked to someone with a shopping problem. The account on your Visa has a yearly interest rate of 14%. That, if you know much about interest rates, might sound really high. It's actually a low interest rate for a credit card. Credit cards are up in the 20s usually. So this is, I took 14% because that was an interest rate that I could get on a MasterCard. I went and looked it up. I was like, what can MasterCard give me right now? And they agreed to give me 14% if I paid all my bills every month. And then the first time I didn't pay my bill, my interest rate goes to 29%. So it jumps up pretty quick. Okay, so this was an actual interest rate problem that I could have done. Question A says create an equation that could represent the amount of money on George's Visa after X years. So we need to try to create an equation. Remember, our equations are exponential like this. Okay. We need to, oh sorry, it's too much.
Give away the answer, didn't you?
No. Yeah. Give her.
Can do 32,000 times the amount of years times X.
Close. You get close.
Exponent of the percentage.
Close. Got a couple things right and a couple things backwards. There's a pretty good shot at it. So this is y equals a b to the power t. Y is going to be how much is on the Visa after some amount of time. So y is going to stay as y. It always does. We talked about this on the first slide. A is usually your initial value, so that's where you're starting at. So A in this case would be $3,200. Now we need a B value. I'm going to put the B value in brackets. Okay, just because I like it to really stick out that it's the B value that's going to the exponent. Your B value is the rate of increase or decrease. So in our case, we're increasing by 14%. Now, the sucker's move would be to put 14. Okay? So that's sucker move number 1. You don't want to put in a percent, you want to put it as a decimal. Okay? So changing 14% to a decimal would be 0.14, which would be sucker move number 2.
Oh my God.
So if you put in 0.14, that means you're going to have 14% of 3,200. If you think about that for a second, 14% of 3,200 would be a smoking deal because that means your amount's going to go down. Right? Think of our graphs. If the b value was less than 1, you were decreasing. We want our b value to be greater than 1. So they're going to charge you 14% on top of your 100%. So they're still going to want the original 100% of your bill plus 14%. So your b equals 1 plus the interest rate.
Now this is on prime.
So it would be 1.14. It can be. That is to the power of. So t is going to be the number of years that have passed. So if this is after 1 year, you put a 1 there. If it's 2 years, you put a 2 there, 3 years, and so forth. You will get questions every once in a while that do monthly, or they do weekly, or something like that. I think we have an example where we talk about that. This one is 14% yearly. Yeah.
So this is the amount of money he has on this visa, and every year he gets more money added.
Mm-hmm. Every year, if you didn't pay any of it, they're going to increase how much you owe. So 3,200 is how much I owe right now. After 1 year, they're going to tack on 14% more to what I owe. Because I'm not paying them back, so they're going to charge me more. Because I'm not paying them back.
How much more would that be?
How much would that be?
After a year.
So after 1 year, if you go
3,600.
32,000 times 114 would be up to 3,600 something.
3,640.
So after 1 year, it's already going to go up to 3,600. This is your equation. You will have to be able to build equations like this one. Okay? There's some you won't have to build, and I'll show you those ones. This is definitely one you'll have to build. Initial value, interest, time. All right, question B. How much will be on George's visa bill after 2 years? So just 2 years of not paying it, that means t equals 2. So y equals 3,200. There's 1.14 to the power of 2. You put that in your calculator, you go 1.14 to the power of 2 times 3,200.
415.
He's going to owe 44,158 and 72 cents. So you can see, like, maybe he bought, I don't know, like a car on his visa for 3,200 bucks. And he didn't pay any of that off for 2 years. Now it's costing him $4,158 just after 2 years. And the other thing that they do for credit cards, like for real life talking, is that this is doing your interest they call compounded yearly. So they calculate your interest every year. Credit cards actually calculate your interest every month. So, oh yeah, you don't need a credit card. Like most people, like
all you really need it for is if you have a big purchase you don't have money for.
Yeah, I use it to get free stuff. Like you can use credit cards for different things, right? So like my credit card, well, one, credit cards are good for like getting hotels because you usually need a credit card to get a hotel. Anything that needs a deposit, you need to use a credit card to use it. And I use it because a lot of credit cards, you can get free credit cards that offer points. So they'll be like, hey, we'll give you a point for every dollar you spend on your credit card. And they don't charge you interest if you pay your bill before the interest period's up. So if you pay your bill before they charge you your interest, they don't charge you any interest because 14% of 0 is 0. So if you do that, you just get all these free points, and then you can buy stuff with the points. Their hope is that if you screw up and don't pay your credit card, they're going to rack in on you. And they're going to make more money than those points are ever worth. Yeah.
Bank accounts have interest rates you get money from? Yeah.
Yeah, so I think we do a question like that. And bank accounts, like a savings account, has interest where they'll pay you money to put your money in their bank.
How much is
It's usually minimal. It's like enough to like cover inflation. Putting your money into a savings account really doesn't make you money. Putting your money into like stocks or something like that can make you some money. But then you might also lose money. It's not a guarantee.
anyone Bitcoin stocks 2000 made a lot of money
Making
now.
a lot of dough, yeah. Okay. The story I was trying to say, sorry, I got distracted, is that they actually compound monthly. So, life lesson is that they actually will take the rate, so 14%, and they're going to divide it by 12 months, and then they're going to charge you every month that percentage. And so that actually costs you more in the long run, because they're going to do 14%, but in little chunks all the way up. But every time they add a little bit of interest every month, then they get to charge interest on their interest. That's how they make more money. Okay, question C. How long will it take for George's bill to reach 5,000? Or 25,000? So we'll do 5,000 together. So if we want the bill to end at 5,000, that means y equals 5,000 equals, then it's our equation, but we don't know the time now because that's what we're looking for. So if I wanted to solve an equation like this, I could definitely log it and put in all that hard work. Or I could say this is y1, this is y2. And I'm going to figure out where those things cross each other. So I put those in my calculator, I go 5,000 is my y1. I'm going to go 3,200, sorry, 3,200, then 1.14, so power of 6. And I'm going to go to my window settings, because my window needs to change. Always do your window settings before you actually hit graph. It's because if you hit graph, you sometimes get caught in this mindset like, I gotta fix the graph I'm looking at. And the graph might not make any sense that you're looking at. So go to your window first, set a good window, and then adjust. X minimum. X is the amount of time that's passed. The least amount of time that can pass is 0. So I put X minimum at 0. X maximum is the most amount of time that you might pass. I'm going to say like 10 years. That's a pretty long time to have a visa until you're not paying off. So I'm going to say 10 years. The scale, I'm going to leave at 1. My Y minimum, that's the least amount of money that I could have on my visa. The least amount of money I can have on my visa is $0. I paid it all off. The most amount of money I could have on my visa, if I look at my question, it goes up to 25,000. Right? So I'm going to say 30,000. And then that way for sure I'll be able to see my answer. My Y scale, I always just leave as 1. But realistically, we could have changed that thing to be like 1,000, so it goes up by thousands instead of 1. If I graph this, I should get a nice little line near the bottom, and then an exponential graph that actually just kind of looks like an increasing line. I might have to bump up my X value a little bit. So my graph looks like this right now. Got one line here. And my line's really not increasing much. You can kind of see it starting to, but it really hasn't taken off. So I might have to adjust my X maximum to see it a little more. So I'm going to change my X maximum to 25. And now all of a sudden my green graph looks good. You can see how fast a visa goes racked up. If I want to figure out when it hits 5,000, I'm finding when they intersect each other. I go second trace, intersect, enter, enter. And it will happen at 3.4 years. Now, according to this question, they only calculate yearly, correct? So, at 3 years, would I be at $5,000 yet? No, I would not. So even though this number would naturally round down, that wouldn't answer my question. My bill never reached $5,000 at 3 years. It's not until the 4th year that it actually happens. So I'm going to say the answer is 4. And it wouldn't be 5,000 exactly, it would be more than 5,000. Right? It would be 5,200 or something like that. But it never hit 5,000 in the 3rd year. You had to wait until the end of the year for it to calculate. So it took 4 years to calculate to get to 5,000. The second one, if you do 25,000, you just have to change Y1 to be 25,000. And then you again are going to go second trace intersect and see where they meet each other. You go second trace intersect. And they would cross each other at 15.689 years. So that means in the 16th year, it would hit $25,000. We'd have to round up. In the 15th year, it's not there yet. In the 16th year, it's there, but it's a little bit more.
So if it's anything over, say, if there's anything over 16, like if it's a decimal or over.
Yep. So if it had been 15.1 years, at the 15th year, I still wasn't at 25,000. At the 16th year, I was. It was a little bit more, but I hit it. Yeah. So you always round up on these types of time questions. Well, it depends on the type of question, right? You have to think about what it means to be in the 15th or the 16th year. All right. My advice to you is to avoid credit card debt to the best of your ability. So this one says, Freddie makes an investment of $7,500 that earns an interest rate of 3% compounded semi-annually. So we're going to have to talk about what that means. It does say right there, note, anything not compounded annually will be provided on a test. So you'll never have to actually build an equation unless the time is like the one we just had, where it's every year. And it's just X as your exponent. Things are going to change a little bit. Yeah. Yeah. The first question is, what does it mean when it says compounded semi-annually? Compounded is like calculating. Okay. So it's like you're calculating the interest. You're adding it on. Annually means every year, so yearly. Semi means half. So this would be calculated every half year. Make sense? So if you ever hear something where they're like, we're going to compound it monthly, that means they would calculate it every month. Compounded annually would be calculated every year. Calculated semi-annually would be calculated every half year. If you heard quarterly, that's another one you might hear, that would be every fourth of a year. So that means 4 times a year they'd be calculating your interest and charging you that interest. In this case, it's an investment, so you want to get your interest. Like, they're paying you interest. That's a good thing. But that's what it means to be compounded semi-annually. It means calculated every half year, every 6 months. Create an equation to model this situation. So this does change a little bit. You'll never have to do this. Okay? You'll never be asked to create an equation that's not just a simple exponent. So this one is y equals, A is my starting amount. So in this case it's 7,500. B is my increase. Okay, this one is, it says 3%, correct? Let's see, 5%? Okay. We said that to get your interest is 1 plus the interest, right? But because it's every half year, that means it's going to be half the amount of interest. They're not going to give you the full 5% every 6 months. They're only going to give you half the interest every half year. So you're going to get 2.5 in interest in the first half of the year, 2.5 interest in the second half of the year. So yearly it's a 5% rate, but every semi-annually it's half that. So this thing would be 1.025. So that would be semi-annual. And the exponent, instead of just being t, it would be t divided by 2. You'll never have to build that equation. Okay. Oh, it would be, sorry, I put t divided by 2, and that's wrong. Because you're getting it twice a year. I should check myself out here. Because it would be happening twice every year. So if in 1 year, you would have had to do it 2 times. That makes sense, like the 6-month mark, and then at the 12-month mark. So it's 2 times t, where t is the number of years. Yeah.
Why is it 1 0?
If you were to change 5% to a decimal, it's 0.05. And divide that by 2, and 0.02. If you put 0.25, that would be 25%, right? And that is a trick. Remember that if it's like a single digit, you gotta have a 0 before it. All right. C. After how many years will Freddie's investment double? It's a good question because it doesn't actually tell you any numbers. You have to figure out what the numbers are. What does it mean if Freddie's investment doubles? It means 2 times whatever he used to have, right? That's what double means. So what did he used to have? He used to have 7,500. If you want to double 7,500, that would be 15,000. Right, so they secretly told you that it was 15,000 by using the word doubles. That's very common that they're going to use that terminology. Another thing they might use is like, when's it half? So if you're getting smaller, then you'd have to know it's half of whatever you started with. Or triples, and that would be times every 3, right? They're not going to always just give you the value. You've got to figure it out. If you want to figure out when that is, then you're going to go 15,000 equals 7,500 to the 1.025 to the power of 2t. And you're going to have to calculate that, y1, y2. So 15,000, and then 7,500, 1.025 to the power of x, sorry, 2x. I graph it with a window that makes sense. Our old window in the last question kind of made sense. Maybe it wasn't that far off, so I just left it the way it was from the last question. But again, time is your years, value is your y. So you know your minimum value is going to be 0, maximum value, I don't know, like 30,000 should be good. Should be able to see that pretty easily. You figure where they cross each other, so you go second, trace, intersect. And you figure out that at 14.0355, it would be at 15,000. So at exactly 14 years, it has not doubled. It's a little bit less than double at exactly 14 years. So that means you're going to have to wait another whole compounding period until it's actually doubled. The answer would not be 15 years. It would be 14.5 years. Because remember that you could compound at every half year. So in this case, you can only round up to the half mark. Halfway through the 14th year, when it compounds, because it compounds semi-annually, that's when it would have hit the double mark.
It would have to be like 14 with no decimals at all.
Yeah, like this one's ridiculously close, but it's still not doubled at the 14th year. You're probably at like 14,900. Like you're so close, but you're going to have to wait that extra 6 months to actually make it happen.
So like on a multiple purpose.
Very possible. What will Freddie's investment be after 6 years? I want you to try to calculate that. So try to figure out what his investment will be after 6 years. So you can give it a shot. Give yourself a second. Think about it. See if you can calculate. So you could have put this into your formula. Calculate it. So t equals 6. So you would have changed the t equals 6. Put that in. Just put that t in as 6. Punch in your calculator, you should get $10,086.67. There's another way you could have done it. Remember your graph that you just did, that exponential graph? You could just go trace 6, enter, and that tells you on your calculator where x equals 6. So remember, you could have just done it right in your calculator. Just for the record, 5% interest rate. If you were to get 5% interest rate from your bank on an investment on a savings account, that's good for a bank. Yeah, that's really good. So you could put $7,500 in there and just let it sit there, and it turns into $10,000 after 6 years. 5% for just a random savings account is actually pretty good. Most random savings accounts are less than that. I think you want like 10% interest rate if you're trying to make investments. I think that's like a good mark for trying to. It's also really hard to do. If you know anybody who's good at investing, they probably make a lot of money because they make other people a lot of money. For instance, whatever Ewan was talking about Bitcoin, that's like investing. So if you bought a whole bunch of Bitcoin when it wasn't worth a lot, and then all of a sudden it's worth a lot, then that's a good investment.
It's like one Bitcoin.
Bitcoin's like thousands of dollars right now, like one of them. Which is our first decaying question. This is the value of a car. So Mr. Kane bought a brand new Camaro for 50 grand. The Camaro's value depreciates every year at a rate of 14.5. So I'm no longer gaining money, I'm losing money. So my graph should look like this instead of like this. Okay, so this is going to be a different looking graph. This is called depreciation or decaying, depending on the situation. Create an equation to model the value of Kenny's Camaro after X years. So I have Y. It's going to be AB to the power of X. A is your initial value, so this is for 50 grand to start off. B is the rate at which you're changing. So before, I was going 1 plus my interest rate. But now I'm losing 14.5%. So I'm going to go 1 minus that interest rate. And again, I've changed that interest rate into a decimal. So this would be 1 subtract 14.5. So that would be 0.855.
Yes.
To the power of X, or T, whichever you want to call it. Those are equations you'll have to be able to make. Okay, where it's as simple as just add the interest or subtract the interest, put it to the power of X. Question B and C, I want you to try to answer on your own. So 3 years, I know the bell's going to go, just give me 1 second. So after 3 years, it should have gone to 31,000. 251. So you can see how fast the car depreciates. Like it loses its value quickly. When will the car be worth $1,000? You should graph that thing. So you'd have $1,000 as the Y1, and then the equation is the Y2. And figure out where they cross each other, and that would tell you your time.
Technically,
I'll put the answer on here. It would take 25 years to be crossed. 24.97.